Okay, so our last example right here is to find the extrema and points of inflection, if any exist, of our function f of x equals x times e to the x. And we're going to sketch this function. So to find the extrema, of course, what we want to do is we would want to make sure that we knew anything about the function that we could. First of all, we know what happens that x equals 0. This is the kind of graph that passes through. Let me get my pen going here. Hello, pen. 0, 0, right? Because when you put in 0, you're going to get 0 times e to the 0, and that's just equal to 0. So this is the kind of graph that passes through the origin at 0, 0. So let's see what happens with the rest of the function. All right. We find extrema at any point where the function is either undefined, where the derivative is undefined, or the derivative is 0. So we need our derivative. F of x is defined everywhere, by the way. Its domain is all real numbers here. Hopefully you can see why. F prime of x, by our product rule, is going to be x times the derivative of e to the x, which is, well, just itself, plus the derivative of x times e to the x. And that, if you rewrite it one more time, is the same thing as x plus 1 times e to the x. If we are interested in finding extrema are going to occur, generally speaking, where the derivative is equal to 0. Well, where is the derivative equal to 0? If we set x plus 1 times e to the x equal to 0, we have to find a point where either x plus 1 is equal to 0 or where e to the x is equal to 0. And of course, the answer to the last one right here is that there are no such values. E to the x is never equal to 0, but x plus 1 will equal 0 when x is equal to negative 1. All right. So at x equals negative 1, we have a potential extrema right here. We should check out to see what's going to happen with the function. We can use the first derivative test here to determine whether that extrema is a maximum or minimum. By the first derivative test, if we check the sign of f prime by substituting in a number, let's say to the left of negative 1, we're going to get a negative. Try negative 2, for example. Negative 2 plus 1 times e to the negative 2 is negative. Or if we substitute in a number to the right of negative 1, if we try 0, 0 plus 1 times e to the 0, that's positive. And so our function is going to be decreasing up to the point at x equals negative 1 and increasing after that point. And so this has to be a relative minimum. And our relative minimum is going to occur at f of negative 1, which is to say negative 1 times e to the negative 1, or stated as an exact value, the negative 1 over e. All right, so our coordinate point of our relative minimum is at negative 1, comma, negative 1 over e. All right, points of inflection, those are going to occur where the second derivative is either 0 or undefined. So if we take f double prime of x, that's the derivative of our first derivative. So we have two functions here. Multiplied by the product rule, it's x plus 1 times the derivative of e to the x, which is itself e to the x, plus the derivative of x plus 1, which is 1, times e to the x. And in this case, if we work that one through, we can factor out e to the x right here, and we're left with x plus 1 plus 1 times e to the x. And so that would indicate that f double prime of x is x plus 2 times e to the x. Well, if we're interested in points of inflection occur wherever the second derivative is equal to 0 and f double prime is equal to 0 at x equals negative 2 only. And hopefully you see why. It's a very similar reason why x plus 1 times e to the x is equal to 0 only at x equals negative 1. Now, it will be a point of inflection if and only if to the left and right of x equals negative 2, that second derivative changes its sign. So we need to look at the sign of f double prime. The sign to the left of negative 2, if we put in negative 3, for example, negative 3 plus 2 is a negative number times e to the negative 2. That's positive, so that's negative. Substituting a number to the right of negative 2, like, say, 0, gives me 0 plus 2 times e to the 0. That's positive. So we have a shape that is going to be concave down, that is to the left of negative 2, and then concave up to the right of negative 2. So there is certainly a change in concavity right here. And so we definitely have a point of inflection here at x equals negative 2. And if we're looking for the coordinate of that, we go back to our original function. F of negative 2 is going to be equal to negative 2 times e to the negative 2, or stated another way, our point of inflection is going to occur at negative 2 over e squared. All right. As far as sketching the function goes, this one isn't too bad. We can sketch that function on our x and y axis system here. I'm going to just generate an x and y axis system here and drag this on down here so that we can see it in action. All right. We said that this function was decreasing all the way up to negative 1 and then increasing after negative 1. We said that our derivative, our second derivative, told us that the function was concave down all the way to negative 2 and then concave up thereafter. We said that this graph passes through points like 0, 0. It has a domain of all real numbers. It passes through negative 1 over e. That's a fraction like probably right about down here. And negative 2 over e squared, kind of like this. I would point out that as x tends to negative infinity, if you were to take your limit as x tends to negative infinity of x times e to the x, we're going to get 0. I'm stating that without proof, but we're going to have a horizontal asymptote to the left. It's going to decrease, being concave down all the way at a point, then decrease and be concave up between negative 2 and negative 1 to this relative, and now we know absolute minimum, and then increase without bound off to the right. So we're going to get this shape, and here is the look at our function, which kind of verifies exactly what we're saying with our points of inflection and our relative slash absolute minimum point here and our intercept. And so we're done.